Hello everyone, this is online course and today we are going to enter chapter 3. Before enter chapter 3, I have a slightly note from the previous chapter, and we talk about the Biot number and Newson number and what's their definition, as you can see on the screen. And then some of the people might find confused if the Newson number is talking about, or the Biot number and Newson number is talking about the relation of the convection. Why there's still K inside? So let me take an example here. So consider you have a ball, a heated ball. Then there's a temperature going to transport to the outside. And from the outside, you have air or liquid, which have the convection. And in this case, if you consider there's no such obvious floating or fluidic behavior nearby the heated spherical, then you can just use the Biot number to consider or to compare the conduction and convection, which is dominate in this case. But if you think about the fluids, the convection now is floating fluids like water. And then in the water, we know there's a boundary condition called slip condition if the liquids touch to the solid. So the boundary condition is look like this. If you have a plate, so consider there's a plate, and if you have a fluids, then you have layers of the boundary. So this we call the boundary layer in the fluid dynamic. Okay, so at the position which very close to the bottom surface, like to the solid. Let's do it like this. In this layer, we call non-slip condition or no-slip condition, which means the velocity of the fluid here equals to 0. So if you want to draw the velocity profile here, so it will become like this. So it will become like this because of the viscosity, and the velocity will decrease, and at this point the velocity ideally will become 0. So this will be the same situation when we talk about the heat transfer when it's heated object inside of the floating liquid. So you can consider a heated ball, then the heat going to propagate from the solid to the outside fluid. But if you got very close look to the object and at this position, really close to the surface, in this region, the velocity didn't exactly move. Regardless, is by active moving or either by density change, then they have a convection. So in this part, the U equals to 0 as well. So in that case, you might need to use a Newson number to verify the situation. But the detail we will go into it when we touch to the convection section. So just something to remind you what's different from the Biot number and Newson number. Okay, so now we officially move to the chapter 3. So the chapter 3 talk about the thermal resistance. So it's like electronic circuits. We take the character also R as resistance. So why we using or we define something called thermal resistance? Because in chapter 2, all the equations start from PDE, the heat equation, if you guys remember. Then through some of the boundary condition and initial condition, we are able to simplify the question into ODE. But still, you need to separate the parameter, for example, dt, dr, or dx, blah, blah, blah. Then, and also through the boundary condition, then you are able to find the temperature profile along the axis. Then from that, you got the heat flux or the amount of the heat. Okay, so that's what we learned from the chapter 2. But what if I didn't care about the temperature profile? Okay, so I just want to know what's the temperature on the surface or exactly in the middle at the interface. Then, for example, if I have a wall covered with some material, unknown material, and I don't really care about what's actually inside. The temperature profile will look like this, or the slope or something. Things I only care about is the temperature 1 and the temperature 2 at the surface. So what we learned here, this is chapter 2. And what we want to get on the surface, that's something chapter 3 could help with that. So which means in this chapter, there's no PDE. Chapter in the heat transfer. Okay, so we're taking the concept from the electric circuit. Okay, let me write down circuit. So if I have a potential V1, which is higher, so high potential, and here is lower V2 potential, then if we connect together, then there would be a current like this. Okay. Then in the middle, we will have the resistance. Okay, so from the Ohm's law, and then we know the resistance can be defined with the difference of the potential divided by the current I have. And in this case, the potential, we can consider this is the driving force. Driving force to push the electron from left-hand side to left-hand side to the right-hand side. So similar concept from the heat transfer. You have an object which have a higher temperature inside, so the T is higher. Then outside the T is lower. Okay, so in this case, the heat is going to propagate from high temperature to low temperature. Then in that case, the resistance, the thermal resistance, we can define, let's take this thermal. We'll define the degree or the difference of the temperature from the high to low and divide by Q. Okay, so the temperature difference divided by the rate of the heat, the transfer rate heat. Okay, and this is also remind us in the fluid dynamic again. If you have a tube, then it must be a pressure drop. So this would be high and this will be low. Okay, then you drive the liquid from the left-hand side to the right-hand side. And this we call Hagen Poisson. Oh, that's a very long Poisson law. Okay, so the Q, this we define as a flow rate. If you remember, that would become the pi d square 4 and 128 viscosity and delta P and the length of the tube. And the fluid resist is also defined as the P and the flow rate. This we call Liu Zu. Okay, you can see the form is quite similar among these three topics. So in the electric circuit, the driving force divided by the current then defines as resistance, and in the fluid dynamic, the pressure divided by the flow rate, we call the fluid resistance. So same as the heat transfer, the temperature difference divided by the Q then equals to the thermal resistance. Okay, so that's the definition of the thermal resistance. Okay, so in this chapter, we're going to talk about the different phenomena, including conduction, convection, and radiation. In that case, three kind of different heat transfer mechanism, and how can we convert the problem into the thermal resistant orientate, then we can solve it relatively easily and not using the PDE or ODE. Okay, so before that, we need to give some assumption. Okay, that's an assumption before we start to driving loads stuff. So first, it should be a steady state. Okay, that would be easier. Okay, and second, similar, the K, the conduction coefficient, must be constant, and same as the convection coefficient, H, is constant, and there's no heat generation. Okay. So we will start with the conduction and also convection, and later on we will combine them together. And in terms of radiation, yes, they have thermal resistance for the radiation, but it is relative use because the radiation didn't count the medium to propagate the heat. So we will mainly focus on the conduction and convection. So first we talk about the thermal resistance of conduction. So the R of the conduction. So we can start to consider a wall, a composite wall. So with a different material that's drawn with different colors. So A, B, C. Then they do have the thickness. Okay, so which means we need to consider the area here. Okay, so the heat is going to propagate from the left-hand side to the right-hand side, the Q. Okay, then let's write down A, B, C. Then they have a different conductivity coefficient. Not a conductivity, conduction coefficient. So they will be Ka, Kb, Kc. And the thickness is also different. So although here I didn't emphasize the thickness is different, but you can consider the thickness will be vary. Okay, and the surface temperature on the left-hand side we defined as a T1, and to the right-hand side we defined as T2. And at the intermediate, then we define like TAB. Here will be TBC. Okay. Okay, so from what we learned at previous chapter, we know the heat is going to propagate uniformly from the left-hand side to right-hand side because this is a steady state. So what we can write is from the material A, the Q divided by the area will equals to minus Ka. Sorry, the Ka means the conduction coefficient, not the area, because we already divide the area in the front. And TAB minus T1 and divided by LA. And for the material B, similar. Let's just write it down again. TKB, then TBC minus TAB, and this is LB. And the material C, QA minus KC, T2, minus 2 BC, and this is LC. Okay, so since this is steady state, so let's assume this is 1, 2, 3 equation. So 1 will equal to 2 will also equal to 3, right? Okay, so which means the term now looks like, let's roll it like here. That would be slightly, okay, Ka T1 AB LA equals to KB TAB minus 2 TBC LB equals to KC TBC minus T2 LC. Okay, so because this is steady state, so now we need to use the property of the sum of the ratio. So that's what you learn from elementary school. So if you got something like this will be equals to this and will equals to this. Okay? Okay, those are the 50%. In this case, because of the property of the sum of the ratio, then you can write it down like this. So you can combine the upper part and divide by the lower part, then you will still get the same answer. So this is the property of the sum of the ratio. Okay, so we can apply this to the equation we have right now. So then that will become, let's roll it like this. Okay, so the Q will now equals to, let's put everything together, T1 minus TAB plus TAB minus BC plus BC minus T2. So you basically put the upper part to here, okay? And then the bottom part is the same. So we put we move the K to the down part, and also the area, we'll put it back. Okay, so there will be LA KAA plus LB KBA plus LC KCA. Okay, so now we try to then what you get, the upper one is T1 minus T2. And the down part, I really don't want to write again. The bottom part will directly become the R. That's the definition of the thermal resistance. Thank you for those information. Okay, so they will become 总温差除上总热阻. Okay, so the yellow part which I highlight, that will be the total resistance, only conduction. Here we only describe in the conduction. Okay? Okay, let's give it a break.